Good day, doctor. My name is Jeffrey Chongzhenzen. My metric number is 225,697. So today we will have an overview of first law of thermodynamics and second law of thermodynamics. So this presentation will start with introduction of thermodynamics, followed by first law of thermodynamics as well as second law of thermodynamics, and eventually I will provide a short conclusion. Let's start with introduction of thermodynamics. Basically, thermodynamics is the science of energy that discusses how energy is used and transformed from one form to another form in their dynamic environment. In thermodynamics, there are four laws, and only the first and second law of thermodynamics will be further discussed. Let's continue with first law of thermodynamics. First law of thermodynamics is commonly called the law of conservation of energy, which states that energy cannot be created nor destroyed. It can only be changed from one form to another. In first law of thermodynamics, the energy transfer that occurs in closed system and control volume will be further discussed. Next, let us discuss about the forms of energy involved in thermodynamics. So basically, we have two forms of energy, which is macroscopic energy and microscopic energy. Macroscopic energy refers to kinetic energy as well as potential energy, and microscopic energy refers to internal energy. Basically, kinetic energy is the energy that a system possesses as a result of its motion relative to some reference frame. The higher the mass or velocity of a system, the larger the value of kinetic energy. Whereas potential energy is the energy that a system possesses due to its elevation in a gravitational field. Potential energy directly proportional to the mass as well as elevation of the system. So actually, there's relationship between kinetic energy and potential energy. For example, if you raise a hammer, the raised hammer will have a high potential energy since it has the potential to go higher or lower. When we hit the hammer on the nail, the potential energy will be transformed into kinetic energy as soon as the hammer hits the nail. Then the kinetic energy will change into potential energy again. After talking about the macroscopic energy, then we will continue with microscopic energy. Microscopic forms are those energy that are related to the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frames. The sum of all the microscopic forms of energy is called the internal energy and is denoted by U. Next, we will continue on the topic of energy transfer. Actually, you could see that kinetic, potential, as well as the internal energy can be transferred into heat and work in closed system and open system. Then, how is actually energy transfer to heat occur? Heat basically is an energy that is transferred between two systems as a result of temperature difference between these two systems. This means that both systems are located at different temperature so that heat transfer can occur. Then energy transfer in the forms of heat will not happen when the boundary of the system is coated with insulated material. Lastly, I want to mention that heat flow into the system, either the system is open or closed, it will show a positive sign, while the heat flow out of the system, it will have a negative sign. After that, how is actually energy transfer to work occur? Work is an energy transfer associated with a force acting through a distance. Work can also be said as an energy interaction like heat that occurs between a system and its surrounding. If the energy crossing the boundary of a closed system is not heat, it must be work. So work involved in a closed system is called boundary work, while involved in an open system is called flow work. Then the work done by the closed or open system is called output work with a positive sign and vice versa. Then in this section, we'll talk about the equation of first law of thermodynamics. So basically, we will have two equations, one for closed system, one for open system. And the difference between those equations are the equation in closed system involve the change of internal energy, while the equation in open system involve the change of enthalpy. Now we'll talk about the first law of thermodynamics in closed system. The below process is the process that will be discussed later in the next slide. The first process is adiabatic process. Adiabatic process is a process that shows that the system does not exchange heat with the surrounding, which means that the net heat transfer is zero. Refrigeration system is one of the examples where adiabatic process occur. In a well-functioning refrigeration system, the condenser will release heat to the refrigerant that passed by, while the evaporator will absorb heat from the refrigerant. There's no heat exchange by the refrigeration system with the environment, as the heat exchange process occurs within the refrigeration system itself. The second process is isobaric process, which is a process that happens when the pressure remains constant throughout a process. One of the systems that apply isobaric process is the boiler system in power plants. At constant pressure, the heat transfer efficiently drives the phase change from water to steam. If pressure fluctuates, the boiling point of water will also change, leading to inefficiency and inconsistent steam production. The third process would be isothermal process that generally occur when the temperature of a process remains constant throughout the process. In real life, an isothermal process was discovered to occur in industrial air compressor to prevent excessive temperature rise during compression in order for reducing energy loss. Then the fourth process is isochloric process. This process will cause the boundary remain constant and thus no work is done on the system. The isochloric process usually happens in constant volume gas thermometer, internal combustion engine, as well as the nuclear reactors. Then the last process will be polytropic process. That is a thermodynamic process that follows the specific equation, which is PV power n equals to constant. Polytropic process are most commonly used to describe process involving compressible fluids like gas due to their significant pressure volume behavior. Then we'll proceed to the first law of thermodynamics in an open system. It involves nozzles and diffusers, turbine and compressor, throttling valve, as well as mixing chamber and heat exchanger. For nozzle and diffuser, nozzle is a device that increases the velocity of a fluid at the expense of pressure, while diffuser is a device that increases the pressure of a fluid by slowing it down. So the heat transfer, as well as the work, potential energy, and the kinetic energy is assumed to be zero for these devices. Then for turbine and compressor, turbine is a device that produces work output, whereas compressors are capable of compressing the gas to very high pressure, which require work input. Then the heat transfer for turbine is assumed to be zero since they are typically insulated. Then the potential energy and the kinetic energy is also assumed to be zero. Next, we'll talk about throttling valve. Throttling valve are any kind of flow restricting device that cause a significant pressure drop in the fluid. Some familiar examples are ordinary adjustable valve, capillary tubes, and porous valve. Throttling valves are assumed to be adiabatic, which means there's no heat transfer occur. Besides, the work done for throttling valve is also assumed to be zero, as well as the potential energy and kinetic energy. Then the lastly is mixing chamber and heat exchanger. Mixing chamber are devices where two moving fluid streams exchange heat by mixing different fluid, while heat exchangers are devices where two moving fluid streams exchange heat without mixing. Mixing chamber are usually well insulated, thus heat transfer is assumed to be zero, while heat exchanger involve heat transfer. Then the work done for mixing chamber and heat exchanger is assumed to be zero, as well as the kinetic energy and potential energy. After talk about the first law of thermodynamics, we will continue with the second law of thermodynamics. In this section, we'll talk about the introduction of second law of thermodynamics. Basically, second law of thermodynamics was developed to determine whether the process is possible to happen by improving the inadequacy of first law of thermodynamics. Second law of thermodynamics is also used to anticipate the degree of completion of chemical reactions and to establish the theoretical boundaries for the operation of widely used engineering systems. Next, we will discuss about the thesis statement of second law of thermodynamics. Basically, we have two statements, which is Kelvin-Planck statement and Clausius statement. Then eventually we will talk about the equivalence of the two statements in this section. So before we get into what is Kelvin-Planck statement, we need to know how is actually this statement been established. As we know, work is an energy that can easily be converted to other forms of energy, but convert other forms of energy to work is not that easy. For example, work done by chef in the above figure is first converted to the internal energy of the water, then this energy may leave the water as heat. However, transfer the heat energy to the water does not cause the shaft to rotate, which means it does not produce shaft work. Luckily, we have one device that are able to convert heat energy into mechanical energy by the help of working fluid inside it, which are heat engines that are a cyclic device. The work-producing device that best fit into the definition of heat engine is the steam power plant as shown in the above figure, which involves one high-temperature reservoir, low-temperature reservoir, a boiler, as well as a turbine. Usually, the process in a steam power plant starts when the working fluid absorbs heat energy from the high-temperature reservoir and converts part of the heat energy into work. Then the remaining waste of heat will be rejected into a low-temperature reservoir. The process would then operate continuously in a cycle. When we talk about heat engines, you will definitely come to the measure of the performance of heat engines, which are called the thermal efficiency. By introducing the concept of thermal efficiency, it is clear that even under ideal conditions, a heat engine must reject some heat to a low temperature reservoir, which means no heat engine can convert all of the heat it receives to useful work. This limitation forms the basis of Kelvin-Planck's statement, which states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of heat. Kelvin-Planck's statement also can be expressed as no heat engine can have a thermal efficiency of 100%. So the same thing, before we get into what is Clausius statement, we must know how actually its Clausius statement has been established. As everyone knows, it is transferred in the direction of decreasing temperature, that is from high temperature medium to low temperature medium. This heat transfer process occurs in nature without requiring any device. However, if we tend to transfer heat from low temperature to high temperature, we require special devices called refrigerators and heat pumps. Refrigerator and heat pumps, also like heat engines, are cyclic devices that involve working fluid called refrigerant and four main components. There is a compressor, condenser, expansion valve, and an evaporator as shown in figure below. The main objective of refrigerators is to maintain the refrigerator spaces at low temperature by remove heat from the refrigerator space, while heat pump is used to maintain a heater space at a high temperature by absorb heat from low temperature source, such as water or cold outside air in winter, and supply this heat to the high temperature medium, such as house. When we talk about refrigerators and heat pump, it must always come to the efficiency of them. By introducing the concept of operation of refrigerator and heat pump, it's clear that devices that deviate from the natural phenomena of heat transfer must at least consist of two reservoirs at different temperatures. These limitations form the basis of Clausius' statement. Clausius' statement states that it's impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. Eventually, in this section, we'll talk about the equivalence between Kelvin-Planck statement and Clausius statement. The Kelvin-Planck statement and Clausius statement are equivalent in their consequences, and either statement can be used as the expression of second law of thermodynamics. Any device that violates the Kelvin-Planck statement also will violate the Clausius statement and vice versa. It can also be shown that, in a similar manner, that a violation of Clausius statement leads to the violation of Kelvin-Planck statement. Then, in this section, we'll talk about reversible process followed by Carnot cycle. Reversible processes are a process that can be reversed without leaving any trace on the surroundings. To determine whether a process is reversible or irreversible, it should be pointed out that a system can be restored to its initial state following a process. For a reversible process, the restoration is made without leaving any net change on the surroundings, whereas for irreversible process, the surroundings usually do some work on the system and therefore do not return to their original state. There are two factors that cause irreversibilities, which are friction and heat transfer through a finite temperature. After knowing reversible process, now is the term for Carnot cycle. The Carnot cycle actually is closely related to a device called heat engines. Probably the best non-reversible cycle is the Carnot cycle, which proposes that the theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine, which composed of four reversible processes, that is two isothermal, two adiabatic, that can be executed either in closed or steady flow system. The first process in reversible Carnot cycle is reversible isothermal expansion, which keep TH constant by absorb heat from energy source. Then the second process is reversible adiabatic expansion, which cause TH drop to TL. The third process for reversible Carnot cycle is reversible isothermal compression, which keep TL constant by releasing energy to the energy sink. While the last process is the reversible adiabatic expansion, which causes TL rise to TH. Then these four processes will continuously occur in a cycle, and this cycle is called reversible Carnot cycle. Here is the period diagram of reversible Carnot cycle. The area under the four processes above represents the boundary for quasi-equilibrium process. In this case, the area under curve 123 is the work done by the gas during expansion, and the area under curve 341 is the work done on the gas during the compression part of the cycle. Also, the area enclosed by the path of the cycle, area 12341, is the difference between these two work and represents the net work done during the cycle. The last section of second law of thermodynamics is entropy. In this section, we will talk about the introduction of entropy, followed by increased principle of entropy, and finally, isentropic process. Entropy can be viewed as a measure of molecular disorder or molecular randomness. As a system becomes more disordered, the positions of the molecule become less predictable and the entropy increases. Entropy is also an extensive property of a system and sometimes is referred to as total entropy, which is designated as S and is defined as below formula. Similarly to energy, entropy is also a property, so it has a fixed value at fixed state. Therefore, the entropy change between two specified states is the same, no matter what path, reversible or irreversible, is followed during the process as shown in below figure. One of the interesting principles for entropy is the increased principle of entropy. Consider a cycle that is made up of two processes, process 1-2 which is arbitrary and process 2-1 which is internally reversible as shown in figure below. This process applies Clausius inequality to find the change of entropy. From the equation developed from Clausius inequality, the inequality sign shows that entropy change for a closed system during an irreversible process is always greater than the entropy transfer. This means some entropy is generated or created during an irreversible process. The difference between the entropy change of a closed system and the entropy transfer is equal to entropy generation, which can be written as an equality. The entropy generation is always a positive quantity or zero. Its value depends on the process, and thus is not a property of the system. Also, in the absence of any entropy transfer, the entropy change of a system is equal to the entropy generation. All processes in the world will generate entropy which is unwanted. Only one process named isentropic process is the ideal process wanted. Isentropic process is a process during which the entropy remains constant. Isentropic process can serve as an appropriate model for actual process. Also, it can also enable us to define efficiency for process to compare the actual performance of devices to the performance under idealized condition. It should be recognized that a reversible adiabatic process is necessarily isentropic, but an isentropic process is not necessarily a reversible adiabatic process. All of all, when applying various systems in the first and second law of thermodynamics, it will definitely come into various technical challenges or conflicts. In this case, achieve high efficiency in energy system often involve burning fossil fuel, leading to greenhouse gases emission and climate change. Besides, large-scale thermodynamic systems also will generate significant waste heat, leading to inefficiencies and environmental impacts. Also, carbon emissions from thermodynamic processes such as steam power plants conflict with society goal for sustainability. To solve the environmental problem without decreasing the efficiency of the thermodynamic system, it is encouraged to shift to renewable thermodynamic cycle, such as solar thermal or geothermal system, which minimize emissions while maintaining efficiency of thermodynamic plants. Implementing cogeneration system that repurpose waste heat for district heating or industrial process is also one way to avoid the use of fossil fuel to increase the efficiency that can cause negative impact to the world, such as greenhouse effect. Thank you for listening.